Plotting values that are obtained through experiment comes with its own challenge when compared with plotting values which are gotten from existing equations. In lesson number 17, let us learn at a stretch all the processes involved in plotting values which are gotten from experiment. Notice what happens, especially at the point of running the line of best fit. Compare it with what you saw when the same thing happened in the case of values obtained from existing equations. Again, it is plotting values gotten from experiment. Now, let us consider plotting a graph for values obtained from experiment. The last graph we plotted had values on the table gotten from a mathematical equation. At this point, let us briefly come to know what this table is all about. A scientist wanted to know how increase in length of a wire causes a change in its resistance. He carried out an experiment, and this table is a summary of his findings. These values came from his experiment. With a setup not shown here and a procedure not described here, he discovered that when he got a particular wire of a given thickness and measured 200 centimeters of the wire, after he tested, he discovered that the wire can cause a resistance of 0.26 ohm. He changed it to 400 centimeters of length and checked again. He now discovered that the resistance has increased from 0.26 ohm to 0.31 ohm. He kept changing the length of that wire from 400 to 600 to 800 to 1000, and he got these resistances. This is a summary of his findings. When the length of the wire is to be measured in meters, we convert this centimeter to meter so that 200 centimeters will give us 2 meters. Please be sure that you know how to convert centimeters to meters. 400 centimeters will give us 4 meters. 600 centimeters will give us 6 meters, and so on and so forth. Again, this is a summary of his findings. He would like to know if this wire, whose values are summarized with this table, is to be used for a construction of a device, and that device will be manipulated by means of resistance. He would like to know the formula connecting the length and the resistance. The first thing he has to do is to check whether it is possible to derive a formula from this table straight away. If you check using the style I told you before, you will discover that it is not easy to tell the formula connecting the length and resistance just with this table. Because of that, we are going to resort to plotting the values of L and R on graph. Afterwards, by means of intercept and slope, that is, if we get a straight line graph, we get a formula connecting the L and R. Let us continue. As usual, let us start with the first step of plotting graph, and that is the layout. Arranging the space, arranging the entire span of the graph page. with view to locating the origin. That is what it means to have a layout. So let us have a layout. This table is appended at this point for easy reference so that constantly we can make reference to these values. Notice that the entire table is not here. Instead, just the two columns that will be plotted were extracted, as it were, from the original table so that we can maximize the use of space. Now, look at this layout. It is the conventional cross layout with here as the origin. Do you think that this is a correct layout for plotting these values on this table? Watch again. Certainly, if you are seeing what I saw, you will conclude that this is not the best layout. In this cross layout, we still have the four subaxes: the positive y, the positive x, the negative y, the negative x. All are almost equally apportioned. Is this the type we need? No. Why? Look at the table. We want to plot the resistance on the vertical axis. Is there any negative value of resistance? No. Everything in this table is positive. Therefore, we are cutting off this side as a side we don't need for this work. Again, look at this length. We want to plot this length along the horizontal axis. Do we need this side of the x-axis? That's the L-axis? No. Again, because if you look at this column, we don't have any negative value for the length. Therefore, we also cut off this side. After cutting off this side and this side as being not needed, what then do? We have to adjust this layout so that we can maximize the use of this space without cramping values. Let us see how we can redraw this layout to fit this table. Let's see. That is the layout, the correct layout. It is now an L layout. This side that used to be long has been cut short. From the edge of the graph page, from the left, we gave a distance or a gap of 2 intervals for emergency and for writing the values while calibrating the axis. So, though this is not needed, a short gap was left for the things I mentioned, namely emergencies and writing values on the axis of this L, of this R, while calibrating it. The same thing was done from here to the bottom of the graph page. That is, 2 intervals were cut off. It is never compulsory that up to 2 intervals are cut off from the edges. Sometimes it is practicable to cut off just 1 interval. That is, if you are plotting a graph which you have already determined before plotting. But if you don't know what you're going to see, if you're not experienced in forecasting or foretelling what a equation is going to be for a particular graph, then it is always best to cut off either 2 or 3 intervals from both margins to get this L-axis. So far, this is the layout we're going to make use of. And that is all about the layout for this particular table. The next is choosing and setting scale for them. First, let us label both axes. This is the label for this axis, the L axis, horizontal axis. The length written in capital L, then in bracket the unit, that is in meters. Please be very careful that this unit is not written as per. Don't write over before you write the unit. This length measured in meters is not the same thing as length per unit meter. They mean different things. And I hope you know that the correct information is that this axis contains length to be measured in meters. If you write over, it means length divided by meters or per meter. That is why you have to write the unit in bracket, not as a divisor of that L. Let's see the same thing in the case of vertical axis. For the vertical axis, we have it this way. Resistance to be measured in ohms. Don't write resistance per unit ohm. That might mean a different thing. This written in bracket means resistance to be measured in ohms. Now, step 2. That is choosing and stating the scale. Let us start choosing the scale for the independent variable, the length. Let us see. We recall that the formula for finding scale is approximately equal to h over t. I believe you remember what this h stands for and what this t stands for. Now, as we focus to choosing the scale for this length, let's find the h for the length. 10 is the h for the length. Do you agree with me? Right. That means that in choosing scale for this length, we're going to replace this h by 10. What about this t? Let us look at how many intervals that are available along the horizontal axis upon which we're going to plot the length. Let's find out. Now we see clearly the axis upon which we're going to plot the L. And on it, we are looking for how many intervals that are usable for plotting the values on it. Please join me as I count how many intervals from here to the edge of this graph page. From here to here, 1, that's 1 interval. 2, 3, 4, 5, 6, 7, 8. That means there are 8 intervals available. But it is good that we remember that it is not all the 8 that we should consider usable. It is advised we cut off 1 or 2 intervals, sometimes even 3, depending on circumstances, for emergencies and other reasons. Okay, let us cut off 2 from the 8 intervals so that we consider 6 as being usable. Just 1, 2, 3, 4, 5, 6. That means we have 6 usable intervals on this axis. Let's go back to our formula and substitute 6 into t. Consequently, we see that the scale is equal to 10 over 6. H is 10, t is 6. I hope you remember how we got them, so that if you do the calculation, you see that the scale is approximately equal to 1.7. By this calculation, 1.7 is our scale. But is 1.7 a preferred scale? The answer is no. Why? 1.7 is an odd number. It is a power 10 submultiple of an odd number, 17. What it means is that we can't use this, not because it is mathematically wrong, but because we can't calibrate the axis without punching a device that calculates. Therefore, we have to make sure that we manipulate this 1.7 to give us a preferred scale, or come back to this substitution and manipulate the H or T or both of them so that we can get the actual value which can serve us as a preferred scale. Let me start with manipulating this answer, 1.7. Don't forget that in every case, our first choice of scale among all the preferred scales is a whole number. So we wish that this 1.7 turns to a whole number. Then we ask ourselves, is there any whole number that is near to this 1.7, which is among the preferred scales? The answer is yes. What is that? It is 2. If you approximate this 1.7 to the nearest preferred scale, what you get is 2. That is, if you round up this 1.7, what you get is 2. We therefore write that our scale is approximately equal to 2. Let us see. See the expression scale is approximately equal to 2. What it means is that along this axis, every interval has a value of 2. That is the implication. I hope we remember that we can also get these 2 by manipulating the values of H and T. It is either I push this 10 up to 12 so that when 6 divides it, it becomes the same 2. Or I maintain 10 and bring down this 6 to 5 so that when 5 divides this 10, the answer is the same 2. Whichever way you want it, just be sure that if you have your way, the best or the first choice of scale among all the preferred scales is a whole number. It is when a whole number is not possible and reachable that we consider fractions, especially in 1 decimal place. After which, if it fails, we can look up to other decimal places like 2 and 3. So far, we are happy to see that we have gotten the value of scale for the horizontal axis. Scale is approximately equal to 2. Let's do the same thing for the r-axis, the vertical axis. In like manner, for the r, we have it that the scale is also approximately equal to h over t. Look at this table again. In this r column, what is this h? That is, which figure has the highest magnitude? Is this 0.26? No. It is 0.51. That means that what we're going to write in place of this h is 0.151. What about t? The number of intervals along the vertical axis. Let's find out. We count the number of intervals on the vertical axis this way, from here to here. 1, 2, 3, 4. We keep counting. We keep counting from here. That is why we stopped. 5, 6, 7, 8. We still have more space. We stopped here, so the 8th one, 9, 10. So we have 10 intervals on the vertical axis. 10 available intervals, not necessarily 10 usable intervals. Let's see what you do about it. Consequently, we have it that for the r-axis, that is the vertical axis, the scale, which is equal to h over t, turns to 0.51 over 9. Don't forget that this h corresponds to this 0.51. the figure with the highest magnitude. And this T refers to number of usable intervals. Though we got 10 available intervals, I took a decision to cut off one interval for a reason you will see if you also try it by yourself. I had to cut off one interval, making it 9 intervals usable. You can as well choose to cut 2 intervals off to make it become 8. In any case, if I cut off one interval to make it 9 usable, when 9 divides 0.51, scale becomes approximately equal to 0.057. If you cut off 2 intervals to make it 8, you may end up having 0.08 as the scale. This scale is accurate, but not usable. 0.057 is accurate, but not usable. It is not easy to calibrate the axis without punching calculating device with this 0.057. What do? We manipulate it to fit into what is acceptable or preferred. Already, there is no way we can approximate this to the first choice among the preferred scales. That is, we cannot make any meaningful impact. In fact, we might go into an outright error if we insist on making this 0.057 become a whole number. Therefore, we have lost out of the first choice. We've lost out in our case to use the first choice. So the next is, can we use a fraction that has 1 decimal place? Anyway, if we do that, it might become 0.1. Though 5 qualifies to be pushed up to become 1 to put here, it is far from what is required. If we push this up to 1 to put it here, by the time we calibrate, we discover that just 2 or 3 intervals, you have reached the highest. So please, though it is possible to make it become 0.1, this 5 also qualified to be pushed up by rounding up is not actually going to give us a good result if we make it become 1 and put it here. We have lost out of our first choice of the preferred scales. That's whole numbers. This way, we have also lost out of our quest to make it become a fraction with 1 decimal place. That means that the next best option is a fraction or a decimal with 2 decimal places. Let's try and check if it is possible to make it that way. Scale is approximately equal to 0.057. This contains 3 decimal places. And our next choice is to make it have 2 decimal places. That means it should stop here. That means that this 7, whether it is up to what we have to round up or not, as long as we want to make it 2 dp, we can cut off by rounding down or check up by rounding this 7 up to 1 and putting it here. It is not compulsory that each time we approximate scales like this, that we must use the principles of mathematical approximation of numbers. We do it intuitively. We just use discretion to know the value we need, which is not very far from what is being manipulated. For instance, 0.057 is close to 0.06. If we jerk this up to 0.06, that would not be a problem. 0.06 is not far from 0.057. But consider it that we had done it 0.1. 0.1 would have been so far from what is expected. therefore, be very careful not to push a scale above its actual value to a value that is far from the actual value of the scale. This way, therefore, we'll write this as that scale is equal to 0.06. Let's see it. There we go. Scale is approximately equal to 0.06. So far, we have seen that the scale for the L-axis is 2, and that for the R-axis is 0.06. I believe you followed the procedure for choosing scales for both axes. Next is the calibration of the axis.